This video is going to be about functions and analyzing graphs. We're going to start with talking about real numbers. So we have 5 sets of real numbers. The letters I have shown on the left, we have some examples on the right. Let's try to fill those in. So first we're starting with Q. Q represents rational numbers. Then we have I, which represents irrational numbers. Z, which is integers. I don't know why they chose a Z. Maybe they spell it the Z. Then we have W, whole numbers, and N, naturals. So if we look at Q for rational numbers, we have 0.125, negative 7/8, 2/3. These are numbers that can be reduced to fractions. They can be positive or negative. Different from that, we have irrational numbers. These numbers have a decimal after them, and this decimal, all the numbers after the decimal do not repeat. So when we have square root of 3, we have 1.73205. Pi is a very famous irrational number, 3.1459. The numbers after the 3 point do not repeat. We don't have a pattern. Integers, these are numbers like negative 5, 17, negative 29, essentially a fraction over 1. This can be a positive or a negative number. Whole numbers, these are the same as integers except we are 0 and greater. Natural numbers are the same as whole numbers except we are 1 and greater. So if we look at how these numbers relate to each other, these sets of real numbers, we know that this I for irrational numbers is going to be different from the rest, right? It doesn't have anything in common with the rest. But if we look at natural numbers, we talked about natural numbers. This 1 we see in both natural and in whole numbers. It can also be an integer. So we're going to start with natural numbers being in the circle. Then we'll add, whole numbers outside of that, integers, rational numbers, and all of these are real numbers. Okay, now we're going to be talking about Setbuilder Notation. This is the notation using properties of numbers to define the set. So given all of this mumbo jumbo below, we actually read this as x, the set of numbers x such that, so some x set such that negative 3 is less than or equal to x, which is less than or equal to 16. So such that some properties were given. And then we can also say that then x is an element of some set of numbers. X is an element of some set of numbers. Okay, let's look at an example. So if we're given the following 8, 9, 10, 11 ellipses, which means we're going to repeat that. This set therefore includes all whole numbers greater than or equal to 8. Okay, so let's try to write that in Setbuilder notation. We have x, the set of all x, such that x is greater than or equal to 8. So x is greater than or equal to 8. Then x is an element of the set of whole numbers. So we're going to write x is a set of whole numbers. That really fun W. Okay, let's move on. Next we're talking about interval notation. So interval notation is a notation using parentheses or brackets to describe subsets of real numbers in a given inequality. So when we have parentheses, that means the endpoint is not included. If we have brackets, that means the endpoint is included. So let's look at some examples below. We have a is less than or equal to x, which is less than or equal to b. So x can equal a and x can equal b, right? So that means we're going to be looking at is included. We want to talk about some brackets here. What about x is greater than or equal to a? So it can equal a. We know that x can equal a, so we're going to put a bracket on this side. The largest value we can get to is positive infinity. We can't actually get to positive infinity. It's not a value we can reach. So we're never going to include an infinity value. We're always going to have a parentheses if we have infinity. Next, we're going to look at a is less than x. So x never actually equals a, which means that we'll have parentheses around the a. Also, the other value we have is negative infinity. I should have written that in the other order where we have negative infinity, comma, a. So we'll do that over here, negative infinity, a. And again, we can't actually get to infinity. So we're going to write parentheses, negative infinity, and parentheses a. The last example we have is a is less than x, which is less than or equal to b. For this one, obviously, we can equal b. We cannot equal a. Less than, not equal to. So that's what our set notation looks like for that, our interval notation, excuse me. So functions, when we're talking about functions, we're talking about a relation that assigns each value of x exactly one value for y. So when we can use the vertical line test to check if the graph is a function. Basically what that means is we're going to be looking at different values of x. At one value for x, if we have multiple values for y. So we can take our pencil or a pen, and we can run over any graph we have, any given graph that we think might be a function. We can look at the values for any given value of x using the vertical line test. So we have a vertical line, we have a pencil, we're looking at x values, and we're saying, yes, actually we do hit more than one value for y at some given point x, which means this one is not a function. We look at the second one, we have, again, more than one value of y for some given value of x, so this is also not a function. We move on to the third one, take our pencil, oops. You'll notice we're not hitting more than one value of x for any given, we're not hitting more than one value of y for any given value of x. That means this is a function, check, function, yes. Okay. For this last one, we actually have a piecewise function. So that means for some x is less than some value, for some x is greater than some value, but we can analyze the y, right? If we have more than one y right here, at this x equals negative 2, our y value is still going to equal negative 2 everywhere. We don't have two y values. We have an open circle at this location. What about at x equals positive 3, right? We see that y is equal to 5. We don't have two values. If it was less than 3, if it was any less than 3, we would have a different value. We would have y equals 2. So this is also a function. If these were filled in, this would not be a function because we would have more than one value for y. So the set of all x in the function is called the domain. It's just some vocabulary. The set of all y in the function is called the range. These are all possible x values. Our domain, all possible y values, is called the range. X we call an independent variable. Y is the dependent variable. So functions are written as f of x. We read this as f of x and interpret as the value of function f per some given value x. So we're figuring out this function f when we're given some value x, right? That's why we have x as the independent variable and y as the dependent variable. So let's evaluate some functions for some given values of x. We have the function g of x equals x squared plus 8x minus 24. So if we're going to evaluate that at g of 6, we'll then substitute 6 in for x. So we have g of 6 is equal to 6 squared plus 8 times 6, 8 times 6 minus 24. This is equal to 36 plus 48 minus 24, which is just equal to 60. Okay, so g of 6 is equal to 60. Then we have g of negative 2x. So again, we're going to plug in that negative 2x into our g of x equation. So this is equal to negative 2x squared plus 8 times negative 2x minus 24. What we get here is positive 4x squared minus 16x minus 24. And that's actually our answer. We can't simplify it any more than that. Next we have g of 5c plus 4. So again, we're plugging in that 5c plus 4 for our g of x value. And we get 5c plus 4 squared plus 8 times 5c plus 4 minus 24. Okay, for this one we get 25c squared plus 40c plus 16 plus 40c plus 32 minus 24. This is equal to 25c squared plus 80c plus 24 when we simplify. Earlier we talked about some piecewise functions. Now we're going to examine one of those. So if we're given the function v of t, we can find the speed v given the indicated time t. So for this function, when t is less than, when we have 0 is less than or equal to t, which is less than or equal to 15, our speed, our v of t, is equal to 4t. Okay? When we have 15 is less than t is less than 240, our v of t is equal to 60. So let's look at some values here, okay? If we have v of 5, we're looking at this very first option because 5 is greater than 0 and less than 15. So we're going to say v of 5 is equal to 4t is equal to 4 times 5, which is 20. If we look at v of 16, we are talking about the second option. And this value is just equal to 60. It's not dependent on that t value, so we don't have to plug anything in. The only way it's dependent on that t value is to tell us that it's 60. It's within that range of between 15 and 240. If our value was 15, we would again plug it into 4t. Even and odd functions, when we have even functions, these are symmetric about the y-axis. Odd functions are symmetric about the origin. Let's talk about that a little bit. Let's try to get some axes on here. X, and this is f of x or y. Good lines. Very straight, I know. Okay, so if we were going to graph x squared, it looks something like this, right? And for some value, like 2, we know that we get, so if we look at f of x equals 2, we would get 2 squared, which would equal 4, right? This actually mirrors this graph. So if we looked at the negative side of this, if we looked at negative 2, seems obvious. We would get that same value on this side. We would get positive 4. So if we looked at f of x for negative 2, we also get 4. These values are equal. So the only difference between these two is that one is positive and one is negative. So for an even function, f of x is equal to, we found that out, f of negative x. for any value on the positive side, we get that same value on the negative side for whatever we're plugging in for our x. Our odd functions work a little bit differently. If we looked at x cubed, we get a function that's like this. So it may be difficult to tell, but this area is the same as this area. So you're rotating it about this and then moving it up, or about this line and moving it down. So let's look at some values here. What if we had 2 again? So if we had f of 2 for x cubed, we get 8. If we looked at the negative side of that, we get f of negative 2 is equal to, seems obvious, it's going to be the same but on the negative end. So we can write this algebraically. F of x for an odd function is equal to negative f of negative x. So when we plug in a negative value for that x, we get a negative value for that f of x. You can move this negative to either side. This is the same as negative f of x is equal to f of negative x. Just multiplied both sides by 1. These are equivalent. That's it.